Hello everyone. In this video we will talk about the concept of polarity in a chemical bond. So when we say chemical bond, we are referring to the covalent bond and the idea of dipole moment. See, Lewis theory, right? It was not able to provide insights into how different molecules are having different shapes, and the dipole moment values of the molecules is a concept that has given some kind of an insight or clue into the shapes of the molecules. So the dipole moment values has provided rather insights into the shapes of the molecules, and later more comprehensively the shapes of the molecules were explained by both the valence shell electron pair repulsion theory, which we call in short as VSEPR theory, and valence bond theory. So both the theories will give us the idea of shapes of different molecules. But here we will try to understand the concept of polarity of a chemical bond and what is this dipole moment and how the dipole moment will be able to provide insights on shapes of the molecules. So if you look at the covalent bond, right? So covalent bond, what is it? So if you talk about the normal covalent bond, the atom A, let's say atom A and B, they are forming a covalent bond. Okay, the electrons are contributed one by each of these atoms, and we will say the shared pair of electrons is jointly owned by both these atoms. That is what we will mention about the covalent bond, correct? Now if you look at a covalent bond between two chlorine atoms in Cl2, the bond pair of electrons will be held together equally by both these atoms because they are identical. How about a covalent bond in HCl? In HCl, there is a covalent bond between hydrogen and chlorine, but chlorine is what? More electronegative. As a result, the shared pair of electrons, in fact, if you remember the definition of electronegativity, what is the definition of electronegativity? We will say it is the ability of an atom to pull shared pair of electrons toward itself in a covalent bond. That is how we will define the electronegativity, right? So here what we see is the shared pair will be drifting more close to chlorine because it is what? Highly electronegative. So as a result, what we can see is there is a kind of partial charge that will get accumulated. So the shared pair will not be positioned equidistant from the hydrogen nucleus and then chlorine nucleus, but it will be drifting little bit more close to chlorine. So we can assign, we are not assigning a minus, because if you put a Cl minus H plus means what? Completely the electrons are taken by chlorine like that. But here this is not happening. Only there is an drift of this electrons towards the more electronegative element. So these type of bonds, right? This is also covalent bond. This is not ionic bond. These type of covalent bonds are called as what? Polar covalent bonds. In polar covalent bonds, we will have partial charges. What will be there in case of the polar covalent bonds? There will be what? Partial charges on the atoms. What we see in the case of the chlorine bond, what is this? This we will call as the pure covalent bond. So pure covalent bond means what? On these atoms there will be no charges. So when you look at the covalent bond, we will see either the bonds are what? Pure covalent or polar covalent. And see, pure covalent, when it will be formed? When you have bond between identical atoms, like you see the oxygen double bond, okay, or the hydrogen bond, or a fluorine bond. So only when the bonds are formed between identical atoms, we will have the pure covalent bond. Otherwise what we will have in most of the cases, when you have bonds between different, like say for example in BeCl2, so we have beryllium forming two bonds, one with each chlorine. So what is this beryllium and chlorine bond? Chlorine is more electronegative, right? So the chlorines will have what? Partial negative charge, and beryllium will have partial positive charge, like that. Okay, so we'll see that most of the molecules we have in that the covalent bonds are going to be what? Polar covalent. Okay, one thing we need to keep in mind is the the polarity in the bond will be increasing with what? With the electronegativity difference. So between the two atoms, if the electronegativity difference is increasing, right, then polarity of that particular bond also will be increasing. It becomes more polar. The bond becomes what? more polar. So this is what we need to keep in mind about the polarity of the covalent bond. Now let us bring in the concept of dipole moment. See, dipole moment is a property that is related to electrostatics. Okay, so you will study more about this in physics also, in 12th physics, right? You will study about this dipole. You know what we call is, we will call it actually as electric dipole. What do we call it as? Electric dipole. So what is a dipole? If you have two equal and opposite charges which are separated by a finite distance, you can see what is the distance between the charges, r. This combination of equal and opposite charges, right, is what we call as a dipole. What is a dipole? Dipole is nothing but what it is, a combination of equal and opposite charges which are having some given separation. That is what we call as the dipole. Okay, now every dipole will have a characteristic measurement which we call as the dipole moment. So dipole moment is used to measure the charge times distance between the two charges. So what is the dipole moment? We will generally indicate this with symbol what? Mu. So mu will be equal to what? Charge times distance between the two charges, q into r. So charge, what is the SI unit? Coulomb. And what is the SI unit of distance? Meter. So what is the SI unit of the dipole moment? Coulomb into meter. But we'll have most often we'll use this unit dBi. So what is the dBi? 1 dBi will be 1 into 10 power minus 18 electrostatic unit centimeter, which is the CGS unit, or in terms of SI unit, what is the conversion? 3.336 into 10 power minus 30 coulomb into meter. Okay, so 1 dBi will be equal to what? 1 dBi will be equal to what? 3.336 into 10 power minus 30 coulomb into meter. This is the conversion. Okay, now the dipole moment is a vector quantity. So in physics you will learn about what are these vector quantities. So vector quantities will have direction. The direction of the dipole moment, right, will be taken from the positive. So here we have positive, right? So positive to negative. So that is how we will consider the direction of the dipole moment. Dipole moment vector direction will be considered from where? Positive to negative. So this is what we will consider as the direction of the dipole moment when it comes to the convention in chemistry. Okay, but in physics you will follow different convention. You will learn about it when we go to the electric dipole study in the +2. Okay, so here in chemistry, what is the convention we follow? We will follow that, the dipole moment will be a vector quantity from the positive charge towards the negative charge. Okay, and the value will be what? Value will be charge times the distance between the charges. So here, what is the significance of the dipole moment from the chemistry point of view? So dipole moment will be a measure of polarity in a given bond. So what is the dipole moment representing? It is representing the polarity in a given bond. So more dipole moment means what? Here the charge values are going to be what? Higher, means the more polarity means it will be giving us what? More charges. More charges means dipole moment also will be what? Higher. Okay, so what is the relation we can see? Generally polarity of the bond is high, means the corresponding dipole moment also will be higher. So this is the relation we have between the polarity in a bond and the dipole moment. Okay, now when we talk about the dipole moment in a molecule, so previously what we talked about is the in a bond, what is the dipole moment? In a bond, what happens if you have, like, take the case of HCl itself. No, so we have HCl, this is partial negative, this is partial positive. These are like what? Equal and opposite charges. So we'll have a dipole moment. So here the HCl bond is having a dipole moment. You know what we call it as? We will be calling it as the bond dipole moment. Okay, so what do we call it as? Bond dipole moment. So how do you measure it? It is the partial charge value. How do you measure this? It is the partial charge value multiplied by the, what is the distance between the two charges? What is the distance between the two charges? It is nothing but the internuclear distance, correct? The distance between the nucleus of hydrogen and nucleus of chlorine. Okay, so this is what we call as the bond dipole moment. When we talk about the molecule, right, we'll have two types of dipole moments in a molecule. One is what we call as the bond dipole moment, that is what we were studying before. There is also one more dipole moment which we call as the lone pair dipole moment. What is this lone pair dipole moment? Take the example of say the lone pair present on nitrogen in ammonia. Okay, so forget about the hydrogens for a minute. So here there is a lone pair. This is a lone pair, right? The nucleus of the nitrogen is what? Positively charged. Lone pair means what? They are electrons, negative charged. So you see a dipole moment from the negative so from the positive charge nucleus to the negative charge lone pair of electrons. So this dipole moment is what we call as the lone pair dipole moment. So in a molecule, when we want to talk about the dipole moments, right, we will have the bond dipole moments as well as the dipole moment coming from the lone pairs. So hence we will talk about the bond dipole moment as well as the lone pair dipole moment. Now in a molecule, if we are trying to add up the dipole moments of different bonds or the dipole moments of bonds with the lone pair dipole moments, what we need to keep in mind is that the dipole moments are nothing but they are vector quantities. Say for example, you have a dipole moment of the bond AB. Let us say the value is what? mu1. Dipole moment of the bond AC. What is the value? mu2. If you want to find the net dipole moment or the resultant dipole moment, so let us say theta is the angle between the AB direction and AC direction. Okay, so in vectors physics you will talk about it. If you have two vectors A bar and B bar with an angle theta between them, the resultant is given by what? You have the resultant formula, root of a square plus b square plus 2ab cos theta. So this is what you have as the resultant formula for the two vectors. Now same way you have two dipole moments, mu1 and mu2. What is the resultant dipole? And the angle between them is what? Theta. So the resultant dipole moment mu r can be given by what? Same concept. Okay, what is it? Root of mu1 square plus mu2 square plus 2 mu1 mu2 into cos theta. Okay, if you have many dipole moments, like mu1 is in this direction, mu2 is in this direction, and we have some other thing like mu3 like that, in those cases, right, when we are adding them, we should always follow the vector laws of addition, because what is this dipole moment? At the end of the day, it is a vector. So whenever we are adding, we have to follow the vector laws of addition. Like simple thing, right? If you have, think about it, if you have two dipole moments equal value, so this is mu, this is also mu, but opposite direction. Two dipole moments equal value, opposite direction. See, if you have two vectors which are having equal magnitude A, opposite direction, what will be the resultant of them? If there are two forces acting, equal value, opposite direction, what will be the resultant? 0. They both will cancel. Similarly here, what will be the net value of them? 0. So these are some of the principles of the vector law of addition. So whenever we are adding dipole moment, we have to always follow the principles of vector law of addition and then find out the resultant. Okay, now one of the important applications of this dipole moment is to calculate the percentage ionic character in a given bond. So how are we going to calculate the percentage ionic character? We will start with the HCl example itself. If it is 100% ionic, means what? If this bond is 100% ionic, means what would happen? This would have become H plus, and this would have become what? Cl minus. There is a complete transfer of charge, which means as per the formula of the dipole moment, right? What is the dipole moment formula? It will be, the charge in this case will be what? E. The charge in this case, because each of them will have, this will have what? Minus E, this will have plus E. E is the basic charge. What is the E value? 1.6 into 10 power minus 19 coulombs. Okay, E into the bond length. So this is what we call as the 100% ionic dipole moment. Means we assume the complete transfer of electrons and calculate what is the dipole moment. In that case, the charge will be equal to what? Here 1 electron is transferred, so charge will be what? E. So E into bond length. This is what dipole moment based on the 100% ionic character. We will calculate experimentally what is the measured dipole moment. So for the same bond, we will experimentally be able to get what is the measured dipole moment. So measured dipole moment divided by the 100% ionic dipole moment, measured dipole moment divided by 100% ionic dipole moment into 100. This is going to be the formula for percentage ionic character. What is it? This is the formula for the percentage ionic character. Okay, so what is the formula? Whatever is our measured dipole moment for the particular bond. So we have methods to find out what is the dipole moment. So what is the measured dipole moment value for the bond divided by that 100% ionic. 100% ionic means what we'll do, we'll assume that there is a complete transfer of electron from the less electronegative element to the more electronegative element. Okay, so from there we will be able to calculate what is the percentage ionic character. Okay, so this is one of the important applications of the concept of dipole moment. And the other application is that the dipole moment will be able to provide clues on the shapes of the molecules. So how it will be able to provide clues on shapes of the molecules? If you look at some of the molecules like BCl3 or BF3, CCl4, CO2, we know for a matter of fact in BF3, let's say each boron fluorine bond has, so here fluorine is what? More electronegative, it will have partial negative charge, boron will have partial positive charge. So each boron fluorine bond is what? It is having a dipole moment. It is a polar means what? It is having dipole moment, correct? But what is experimentally found is BF3 molecule has net dipole moment 0. For the BF3, what is the net dipole moment? 0. So in BF3 there are 3 boron fluorine bonds. Each bond has got dipole moment. Okay, so how the net dipole moment could become 0? When the 3 dipole moments of the bonds cancel each other. How they will cancel? If these 3 bonds, right, their dipole moment values will be same. Why? Because it is the dipole moment between the boron and fluorine, values are same. It is like you have 3 vectors equal magnitude and the resultant is 0. How these 3 vectors will be arranged? They will be arranged symmetrically. Means what? If you see, if they are pointing to the corners of what we call as an equilateral triangle, that is symmetrical arrangement. Take off it, right? So if you have a symmetrical arrangement means what? Each of these angles is going to be what? 120. So when you arrange them as if the bonds are pointing to the corners of the equilateral triangle, then what we see, the 3 vectors will net cancel each other, so that the resultant or the net value of the dipole moment will be what? 0. So what we will be able to get as a clue is that the BF3 including BCl3 also should have a shape where these bond dipole moments cancel each other. And what is the shape that we can think of? We can think of the shape which we will study more about this later. So we will call this shape as what? Trigonal planar. Similarly, if you have the case of CO2, so CO2, we know that each of the carbon oxygen bonds has got dipole moment. Oxygen is what? Partial negative, carbon is partial positive. But how these two could be cancelling each other? Because overall CO2 molecule is having 0 dipole moment, which means here if you have a linear arrangement, think about it, if you have a linear arrangement, right, see the dipole moment of the carbon oxygen bond on one side and the dipole moment, remember we discussed about it, right? If you have 2 vectors equal magnitude opposite direction, what will be the resultant of them? 0. So that way in CO2 the bond dipole moments will be cancelling. Similarly, when it comes to CCl4, each of the carbon chlorine bonds are what? Having dipole moment. You look at a carbon chlorine bond means what? Carbon is partially positive, chlorine is partially negative. So these bonds must have what? Each of these bonds must have dipole moment. Each of these bonds must have dipole moment. So overall molecule is not having any dipole moment means what? CCl4 also must have what we call as the symmetric structure. So we will learn more about it when we go to the valence shell electron pair repulsion theory. But the arrangement of the chlorines, right, will be in a shape what we call as the tetrahedral shape. Okay, what is it called as? Tetrahedral shape. Okay, we'll know more about it when we go to the VSEPR theory. But this way what we see is that symmetric distribution of these four vectors. Dipole moment is a vector, each of them has same value or magnitude. Symmetrically when you distribute, right, their total value will be what? 0. This is the principle of vectors. If you have vectors of equal magnitude, they are symmetrically distributed in space. The resultant of the vectors will be what? 0. So this is how the dipole moment of the molecules will be able to provide clue on what could be the shapes of the molecules. But we will not be able to straight away decide what is the shape of the molecules from the dipole moment value, but we will rather correlate it with the subsequent theories of the chemical bonding, like the valence shell electron pair repulsion theory. Okay, we can see some more examples. If we talk about BeCl2 has a net dipole moment 0. So each beryllium chlorine bonds, they have dipole moment. Beryllium is what? Partially positive. Chlorines are what? Partially negative. So the net dipole moment of BeCl2 is 0. How is it going to happen? If you have the arrangement of the beryllium and the two chlorines in linear manner, we can see what? Both these beryllium and chlorine bond dipole moments, they will cancel. So what is happening? The bond dipole moments cancel each other. When they cancel means the net dipole moment will be coming as what? 0. So this is what happens in the case of BeCl2. So what is the clue that we get from here? That the BeCl2 will be having a linear shape, whereas H2O with a similar looking formula, look at it, you have what? Oxygen and 2 hydrogens, but the thing is H2O has a dipole moment. You can look at it. Okay, we don't need to remember what is the exact value of the dipole moment. Here what is it? The value given as 1.84 dBi. Okay, so the H2O is having overall dipole moment, means here it should not be having a linear structure, should not be there. The oxygen hydrogen bonds, oxygen is what? Partially negative, hydrogens are what? Partially positive, correct? So here of course we should have been indicating the directions differently, isn't it? The dipole moment will be from which direction to which direction? It will be from, in chemistry convention, what are we choosing? It will be from the positive charge to the negative charge, like that, isn't it? So what you see here is that the H2O should not be having a linear shape. So later we will see that H2O in fact will have a non-linear shape. So we know what is the, the shape. It should not be linear. It will be having what? A non-linear shape. In fact, in H2O, right, you can see there will be a dipole moment for the oxygen hydrogen bonds, and also the oxygen will have 2 lone pairs. In H2O, the oxygen will be having 2 lone pairs. So there will be the lone pair dipole moments also. So in H2O, what is there? There will be lone pair dipole moment as well as the bond pair dipole moments. Okay, what we see here is that the non-linear structure will mean what? Will mean that the dipole moments are not actually cancelling each other. So this is what we will be able to know from the dipole moments of the molecule. So this will give us some kind of an clue, or rather understanding into the shapes of the molecules. Okay, now just to summarize, what are the applications of the dipole moment? So we have the application of dipole moment to calculate the percentage ionic character in the bond. What is the formula? Measured. So percentage ionic character, what is the formula? It is what? Measured dipole moment, okay, divide by the 100% ionic dipole moment into 100. This is the formula, correct? And also this is used in finding the geometric, not exactly to find, but it provides clues. It provides clues on the geometric shapes of the molecules, like we have seen. When we see that the beryllium chloride has got a net dipole moment 0, means what is it that we will be able to conclude from here? that BeCl2 must have a linear structure. Okay, when we see BF3 or BCl3 has net dipole moment 0, we expect that the arrangement will be what? It will be a trigonal planar. When you see CO2, the dipole moment is 0, means what do we see? Again the arrangement must be what? Linear, like that. Okay, so it will be able to give us some clue on what will be the shapes of these molecules. Okay, so these are the applications of the dipole moment. We have some more applications pertaining to the organic chemistry. Again, we will talk about these applications when we go to organic chemistry. In organic chemistry, right, we have something called as geometrical isomerism. So what is it called as? Geometrical isomerism. Okay, so geometrical isomerism in case of the double bond. So what is the geometrical isomerism? If you have a carbon-carbon double bond, you have a carbon-carbon double bond. Okay, so think about it. This carbon is bonded to a CH3 group and hydrogen. This is bonded to a CH3 group, a hydrogen. Look at this. This is one arrangement. Okay, we'll have another arrangement. A CH3 here, a CH3 here, hydrogen. So these two arrangements, right, what is the difference? When you look at the carbon-carbon double bond, when you look at the carbon-carbon double bond, right, so here we'll have the carbon-carbon double bond. This is the carbon-carbon double bond line. The heavy groups, what are the heavy groups? We also call them as what? The bulkier groups. Okay, so we'll learn more about them when we go to the organic chemistry, but here we just want to get that idea, that's it. Okay, the bulkier groups are what? Methyl and methyl. They are on the same side of double bond, you can see. This geometrical isomer, right, we call it as a cis isomer. Whereas here, look at it, the bulkier groups are on opposite side of double bond. We will call it as what? A trans isomer. So the geometrical isomers, we also call them as what? A cis and trans form. Now if it is a cis, what you see is the dipole moment will be adding. So they are on the same side, they will be adding. Whereas in trans, right, they will be cancelling. So in cis, what you see that the dipole moments are what? Adding. Here in trans, they will be what? Cancelling. So generally, again, here we just need to get that idea that okay, the dipole moment has even got applications in organic chemistry. About this, we will again study in detail when we go to the organic chemistry itself. Here we are just trying to understand that this concept of dipole moment is not just related to the inorganic chemistry, but this is also into organic chemistry. So what we see is generally a cis isomer will have more dipole moment than the trans isomer. So this is what we need to keep in mind. We'll again discuss in detail about it when we go to the organic chemistry. Okay, so in fact when we go to the organic chemistry, right, there we will even take different examples and then try to analyze. We also have one more application in organic chemistry, that is the dipole moment values can even help us in identifying or classifying what are the different benzene derivative forms. What do you mean by the benzene derivative forms? Okay, so if you have two groups attached to benzene ring, let's say, look at this one, if both the groups are on the adjacent carbons, we will be calling it as the ortho form. If both the groups are like first and third, we will call it as what? Meta form, first and third carbons. If the groups are exactly on the opposite side carbons, we will be calling it as the para form. So we'll have ortho, meta and then para. Now the thing is, if you look at the para form, look at it. So here we'll have the group X, here we have the group X. The dipole moments are exactly in opposite direction, isn't it? So what do you see? If both are same group, means the dipole moments will exactly cancel each other, isn't it? They are in opposite direction. So what do you see in this case? The dipole moment will be coming as what? 0, because they will be cancelling. When it comes to the this is the para. Okay, this is what? Ortho. Look at ortho. The dipole moment are having some angle. It is like what? Mu and mu. Both are same value. What is the angle here? The theta is an acute angle. What is theta? Theta is an acute angle. Okay, so the resultant will be given by which formula? Root of What is the resultant formula? Mu r is equal to what? Root of mu 1 square plus mu 2 square plus 2 mu 1 mu 2 cos theta. The thing is, theta is acute means what? Cos theta is positive. But whereas when it comes to the meta, right, look at this. Here, the theta will be what? Obtuse. Obtuse means what? Cos theta will be negative. So we'll see when cos theta is negative means what? Definitely the resultant value will be lesser. So in case of the ortho, the net dipole moment will be what? Higher, because there the cos theta will be what? Plus. Correct. In case of meta, cos theta will be what? Minus. So it will be little bit lesser than the ortho. In case of the para, we will see that they will almost cancel. I mean, if both these are x and x, sometimes what can happen is you can have one of the group attached to benzene as, say for example, chlorine. Another group can be what? Fluorine. If both are chlorines means they will exactly cancel. One is chlorine, one is fluorine means what? They will cancel only to some extent. But generally what we can say in the meta, ortho and para forms, right? The ortho will have a higher dipole moment than meta than para. So like if both these groups are same x and x, if both these groups are x and x, right, what we will see happening in case of para the dipole moment will be what? 0, because it will exactly cancel. So the order is what? Ortho more than meta more than para. So to compare between ortho and meta, what are we doing? We are using the resultant formula. Ortho means what? Cos theta is positive, acute angle. Meta means what? Cos theta negative, obtuse angle. That is where the difference comes. Okay. So this is about the applications of the dipole moment when it comes to the organic chemistry, both in classifying the cis and trans isomers as well as classifying the ortho, meta and para derivatives of the benzene. So this is about the concept of polarity and dipole moment. Again, after VS-EPR theory, right, we will try to understand how the shapes predicted based upon the VS-EPR theory will explain the dipole moment values of the molecules. So we'll have a separate video on that. There again we'll discuss on how, or rather in what way the VS-EPR theory will be able to justify the experimentally observed values of the dipole moments.